So good morning, or good afternoon, I should say. My name is David Kaeli. I'm pleased to be presenting to you today on GPU trends, architecture, and programming. So I've been working on GPUs for almost 15 years, and so we've been doing research on both hardware and software, programming languages, runtimes, applications. And today I'm going to be talking to you about trends in architecture and programming. Tomorrow, I will be covering more advanced topics related to both security and reliability of GPUs, as well as research directions. I'll also talk about GPU simulators. So actually, how do you go about doing research in the field of GPU computer architecture? So that will be tomorrow's lecture. Today, we're going to talk about basics. And so let's begin. Let me just configure myself a little bit here. I'm going to close that. So why have these devices become so popular? They're really the accelerator of choice today. Based on a couple of studies, if you look at the number of active video gamers, this graphic here on the right shows us that there's a continuing trend of the number of active video gamers worldwide. And again, those are using high-end GPUs for rendering 3D graphics. And it may be more of a VR environment. There's also GPUs are used for movie animation. Mid-range and lower-end GPUs can be used for computer displays, and your smartphone has a GPU. There's a variety of manufacturers out there: NVIDIA, AMD. They're both leaders, as well as Intel. Imagination also for embedded, and Qualcomm, and others as well. But really what this has created is it's created a very competitive commodities market. And what's nice about commodities is when things become, the general public is buying lots of these, it becomes competitive. That moves the technology forward. It creates competition. It creates markets that companies are willing to invest in innovation and new technologies. And so you've seen a lot of innovation in GPUs, mainly because of this much larger ecosystem of gaming and graphics generation. That has really been the driving force. More recently, we've seen that has changed a little bit, where computing, so I call it GPU compute, has become a more mainstream application. So let's see. So let's look at some of the reasons why graphics processors have become the accelerator of choice. If you look at, this is a graph that shows 42 years of microprocessor trends. This was developed by, it was on Carl Rupp's page. He actually does some very nice studies on, but it's also data collected by a variety of people. But this is looking at microprocessors, so CPUs. And you look at the number of transistors over the past basically 50 years. It's actually 42 years. And if you look at single-threaded performance, this blue set of points, you're seeing we're maxing out. We're basically hitting some thresholds. While the number of transistors continues, it's getting harder and harder to get better single-thread performance. And also, in terms of device technology, cranking the frequency, well, it's power. It's all about power. It's about energy, and it's about thermal. So we know we've hit a number of walls here. So I think we are looking at what's next here. So again, looking at comparing single precision and double precision performance across CPUs and GPUs. This was taken from an archive article that some of my graduate students have done, where they looked at a number of different devices, both CPUs and GPUs, and they're looking at how scaling across. And this has data from Intel, AMD, and NVIDIA. So what you're seeing is we're seeing some really nice gains in terms of single and double precision performance as we go to more recent architectures. And so we're still seeing some gains. There's some nice devices out now by AMD on the CPU side, but on the GPU side, they're really the teraflops, both single and double, is definitely there and healthy. Again, looking at just GPU power, how is this trend? So we look at gigaflops per watt, and again, you're seeing a nice trend. A GPU, while it's a very energy hungry device, it's also, in terms of performance per watt, a very efficient device. So, and then if we look at just scaling of transistors and density, comparing CPUs and GPUs, again, we've seen where things scale in terms of, and a lot of this has to do with device technologies. We're now at 7 nanometers. We're just looking at the overall transistor counts. I don't think Moore's law is completely dead here, and that's pretty much what this comparison says. And GPUs are able to take advantage of some of these trends as well. I encourage you to go off and read that archive article, because it does make some points. This basically, it's not a particularly, that we're not presenting anything but measurements, public data that's available online, and reporting on it across lots of different devices. So I think it's worth your time to review. Okay, so let's go back to 2007. This is actually a slide I presented in 2007. I've made a couple of edits to it, but it's pretty much unchanged. What was going on back then? So this is 13 years ago. And honestly, the first application I worked on on a GPU, we were using shader languages, and we're basically doing it in OpenGL, the programming, and luckily we saw changes such as the pixel and vertex shaders became a programmable unit, and this changed the game. It made the device much more programmable, where I did not need to know or use the graphics APIs anymore, and I could move to a higher level language, Cuda in particular. AMD in ATI, so ATI was the graphics company that AMD acquired, and but they were making something called Close to the Metal. It was basically an assembly type language for the GPU. Cuda came out and really changed the world. It really made this device something that we could start to program and develop general purpose applications on. So Cuda has matured. So let's roll forward to today. We're at Cuda 11. It's a very mature language. It has a huge amount of library support, tools. Along the way, we've seen OpenCL, which was supported by the Kronos group. So basically, this is an open language standard introduced as a path for heterogeneity across computes of CPUs, GPUs, DSPs, FPGAs. OpenCL delivered on that. Again, we'll cover OpenCL in today's presentation. So I'm not going to describe it much further now. OpenAC was, again, an open standard set of compiler directives, similar to, so think of it as OpenMP-like. And then the Heterogeneous Systems Architecture Community, the HSA Foundation, was trying to develop cross-vendor support for better integration between the host and the device, the CPU and the GPU. And AMD more recently has been pushing their platform. They have HIP and ROCm to support multiple languages on their hardware. So they can run, actually today, you can run Cuda on an AMD GPU. Very exciting. And again, I'll cover HIP and ROCm as part of this presentation today. So let's look at applications, because applications are what drive everything. We can design great hardware, we can create great programming languages, but without the applications that are driving this movement, basically it will be left on the vine to rot. So we do see, in terms of traditional computing, things like FFTs, matrix multiplication, really actually is some of the core convolution. Over here on the right, we've seen some new movement in terms of things that are going to support security and systems operations. So you see, and this provides us with much more heterogeneity in the execution, multiple compute kernels, and also doing things like AES, garbage collection, things that you would think would run on a CPU, but we have this GPU sitting here, and it does things very well if they can be described in a way that's somewhat inherently parallel. So if we can do this, we can get great performance. Some irregular computations such that involve synchronization, things like sorting, histogramming. Nested parallelisms become where we can do graph search, and we can do recursion. So over here on the left, we have down at the bottom signal processing. That's been around, and where we've done a lot of filtering. Those are very natural applications for a GPU. Because they usually involve some nested loop structures that map very nicely to the GPU. And then here in the orange box, this is really where we are today. Is a lot of machine learning is now running on the GPUs, doing both training and inference. A lot of it involves data-dependent kernel launches based on the nature of the model that's being used, the layers, the sparsity of the actual computations. So there's a lot of what we refer to as fragmented parallelism, because it's this is an iterative type of environment where when we're doing training, and the computation can change while the layers may be the same over the execution. There is some fragmentation. And so, and again, we're seeing this in CNNs, DNNs, all kinds of AI and machine learning applications. So in that space, here's a graphic from NVIDIA, basically for their P100. So this is their Pascal line, and it's comparing against some of the Kepler devices and also a CPU. This blue line is what CPUs can do. The gray is what their Kepler device can do, and then they show for various workloads what the latest NVIDIA devices P100s. And what you're seeing here is the move toward getting some speed up across different application domains, whether it's HPC or machine learning, as we, as you add the number of GPUs. And that will be part of what we discuss here today is, those paths of getting to multiple GPUs. We'll also discuss some of that tomorrow when we talk about our simulation. So today we have, some of the fastest GPUs, the AMD Radeon Instinct MI50. I just bought a cluster that has 112 of these installed, which is very nice. And can't wait to start cranking up some interesting applications on it. It has 3840 cores, so with lots of memory, and again, lots of bus bandwidth, so it can do natively. Double precision is 6.7 teraflops. Their single precision is 13 teraflops, and their half precision is 28 teraflops. So, a pretty aggressive, nice design that sort of doesn't optimize for just half precision or machine learning, but can do still single and double precision as well. If we look at, this is again another NVIDIA graphics, a little fuzzy, sorry about that. But if we look at how we scaled in terms of different devices, so things that really came into play. So Pascal was sort of an inflection point in the GPU space in terms of introducing things such as mixed precision, new memory technology, as well as NVLink, which I'll describe in just a second, which allows for scalability between multiple GPUs in terms of communication. Volta this is where we are today. Volta is really optimized for doing, sparse gem. This is sparse gem per watt, is this particular graphic. If we look at some of the specs between these devices, we see continued, you'll see something called compute capability, and that talks to what version of the runtime drivers that are supported in the language features. So, you'll see this mentioned from time to time. This is the number of threads per watt, per warp. Sorry, per warp. And again, some of these things stay the same. Some of them change, as you can see. But as we go generation by generation, so how many 32, floating point 32 single precision per shared multiprocessor, this is getting smaller. So, and then there's the ratio of SM registers to FP32 cores. This is increasing. So, you see different trends. And again, the shared memory size, which we'll talk about what shared memory is. So this changes per generation. A lot of things I'm going to present today will be for a version of the GPU. I'm actually going to focus on the Kepler. But the same things are present on all GPUs, and there will be differences depending upon which GPU you're on. So I'll mention that from time to time. Here's the A100. This is the latest and greatest from NVIDIA. So, now this is really focused at providing what's been introduced is tensor cores. So basically they focus on, the tensor core scalability. So if you, based on the matrix size, this is doing mixed precision matrix multiplies, which is the core of a lot of deep neural networks in terms of the computations. So you have, in terms of, FP16, you have, and NVIDIA's got their own formats in terms of different floating point formats. So, and again, you're seeing the blue down here is their double precision. So they've given up some space and some room on double precision to get some of the tensor processing running very efficiently. And so, you know, it's a trade-off. So one big thing I always say is, just want to check messages here. Okay, I see I have some chats. Everything's good. Okay, thank you. So by the way, today we're going to go for a while, probably about an hour, and then I'll take, I'll stop and ask for questions, and then we'll take probably a 5-minute break. We'll resume. Again, we'll do the same thing, go for, you know, 45, 50 minutes, stop, ask questions, and then that'll be the end of today's session. Tomorrow's format will be slightly different. So in terms of at the consumer level, so if you look at consumer cards, so some of the things I just presented are really the, you know, the Tesla series. They're sort of, you know, server data center class systems. We look at what's available to the gamer, we can still actually run, you know, CUDA, OpenCL, other languages on these devices. I call this world flattening technology. These are little mini supercomputers that I can have in my desktop, and for anywhere from, you know, $200 to $1,200 or, you know, or euros, you're basically seeing, you know, a device that can do a lot of work that a whole data center could not do before. And so, again, this is changing who actually gets in the game of high performance computing, who can actually run, you know, machine learning models. You know, everyone can, and that's great. I think that's a really important message in terms of thinking about GPUs. Okay, so next I'm going to talk about some GPU architecture basics. So this part, I'll cover the architectures, and then I'll take that break and allow you to ask questions, and then we'll move on to programming languages. Okay. So if we want to get high performance on a parallel system, we can you know, improve the speed of the computation, so we can design, you know, a better core. But the problem is we need to feed the core. We have to give it instructions, we have to give it data, so we need some way of hiding memory latency. So we like to, and if we're doing things in parallel, well, maybe we can do this through having lots of threads and then pipelining access to memory. We also want to limit or hide communication overhead. So communication where we have to synchronize, or we need to, you know, one part of the computation has to talk to the other part of the computation, and maybe one has to wait, and we get to synchronization points and other things. We really want to limit this. So two major ways, there's actually more than two, that we can achieve these goals is through architecture and microarchitecture. So the core and system design, we can optimize, so we can go parallel. We can go with, you know, sort of a vectorized, an SIMD class of architecture, where we have, you know, single instruction, multiple data, or SPMD, single program, multiple data type of execution. The memory hierarchy, we know from CPUs, we can build big, large caches. And so, you know, and we'll do this per core, but we have thousands of cores on a GPU. Can we build that same kind of memory hierarchy for each of these cores? Maybe not. Maybe things change. Other ways we can get performance is basically through parallel programming. That is efficient languages and compilers, as well as an efficient runtime for managing, scheduling, and hiding latency. So let's talk about the general architecture of a GPU. I refer to it as a many core architecture, versus a multi-core. So thousands of cores, the types of cores that we would think about on a multi-core CPU. Today's systems on the microprocessor side, on the CPU side, generally have some number of CPUs, maybe 1 to 4 CPUs, where that CPU will have multiple cores. Those cores can run threads. Each core will usually have its own L1 cache share at the L2 level, and then a system-wide L3. And they're all sharing shared memory. Coherency is enforced across the whole device. And so there's a lot of extra, and there's, these types of architectures tend to be what I refer to as cache heavy, worried about single threaded performance, not throughput necessarily of the whole application, but let's get this one thread running really well. So we're going to provide for a significant amount of dealing with control being mainly conditional and unconditional transfers, branches, making that run fast. And that, because we can't run fast if we don't have the right instruction path. So we have to be able to predict and keep the ALUs all busy. We have deep memory hierarchies to hide the latency. We're trying to, and again, because it's a long way to get to DRAM, but this can do well with irregular data accesses. There's more cache, more control, and so that can scale nicely for single-threaded performance. GPUs are designed around massively parallel, and they're throughput-oriented. So I'm going to have much simpler in-order pipelines where they're going to be doing a lot less complex things. We don't have the concept of branch prediction on a GPU. We don't have the concept of a lot of out-of-orderedness in terms of instruction execution. So, and we can deal less with, so I show the control as being very small and the caches being very small, in the sense that while we do have caches, they're dedicated for different purposes, and they're, it's not general purpose. There is some coherency, but it's local coherency, and again, it's limited coherency. And there's at least sharing going on, I'll say, but there's not what we would think of as cache coherency in any real fashion. It's, so sharing and communication is handled by the programmer. So this gets a lot more complicated and a lot more challenging. So if we look at how architecture is designed, we basically have, we start with, and this is where, again, we're going to talk Kepler here. We're going to talk about streaming multiprocessors, where you think of a GPU architecture as a hierarchy, and that hierarchy begins with a core. So a CUDA core will have a floating point unit, an integer unit, but again, a fairly simple pipeline. There's also, in addition to a CUDA core, there's load store units and special function units. So, and a certain number of these will be combined to make up what we're going to refer to as a streaming multiprocessor. Okay, so again, a certain number of these get combined together, and then they're under the control, and then they have associated with them register files, instruction caches, everything else. So Again, we're going to build this hierarchically. So, so the streaming multiprocessor has CUDA cores, shared memory, a register file, load store units, special function units, and a warp scheduler. So a warp is the unit of computation that's scheduled on the GPU. So think of it as, and again, you're going to be sending, so it's a set of threads. Usually it's either 32 or 64, depending on which architecture you're on. And so you're going to be scheduling these and swapping these in and out. And you can do thread swaps very efficiently on a GPU. That's one of its major attractions. That's how it hides memory latency, because it doesn't have a lot of memory as compared to the number of cores. So it's really good when you can feed it with, it can do processing without having to access a lot of memory. That becomes more challenging, and that's when we would like to stream memory to the cores. But sometimes those cores we have to swap out a thread on a core, so based on what data is available in my shared memory. So again, execution of hundreds of concurrent threads just in each SM. We have multiple SMs per GPU. So the K40 Kepler has 15 multiprocessors, so 15 SMs and 192 CUDA cores per SM. So you get a total number of 2880 processor cores. So that's a lot of cores. What are we looking at on CPUs today? 32 or 64 on the high end. So again, some contrast there. Nice thing about a GPU is you can query the device and get information about what's installed, and it can tell you everything from the version of the CUDA driver, and it tells you how much memory, global memory, number of CUDA cores, etc. So very nice utility that's provided in CUDA. We'll be covering CUDA later on. The K20 has 13 SMXs, so they're enhanced SMs. And in this time frame, NVIDIA introduced two key features, one being dynamic parallelism. So dynamic parallelism is that after I issue a call to a kernel on the GPU and it's running on the GPU can decide, oh, well, I have more work to do. Let me spawn some work for myself to do. Instead of having to go back to the host, that communication back and forth to the host, that's expensive. We talked about one of the ways to reduce the overhead of to get better performance, we want to reduce communication. So dynamic parallelism is a mechanism for reducing that communication, supporting things like recursion and algorithms that are have some data dependencies within them. HiPEAC is a feature that was introduced that basically allows you to run concurrent kernels. So now I can run two things concurrently. Let's say I have kernels that don't use the whole device. I can run them concurrently and share the device. And again, it gives me some capabilities to get some overlap of execution from different kernels as they run. They also provided for some added features in terms of atomic operations, and I'll cover atomics later on. So dynamic parallelism, again, I mentioned this, so GPU side thread spawning, support for recursion. So, instead of this back and forth communication, now I can do, just one call and let the GPU figure out all the extra work it has to do dynamically, make those decisions, and then return the result to the CPU. So again, in the SMXs, it has 192 CUDA cores, 64 double precision units, 32 special function units, and 32 load store units. So a little different than the earlier one. And SMX has 4 warp schedulers. This, again, so this warp, which is the number of, so you have 32 threads per warp for this particular device. You can have 4 scheduling engines being able to, so 4 warps can be issued and executed at the same time. And again, but you can only do that if there's enough resources, particularly registers, available for actually doing that execution. So if you have 64 warps and there's 32 threads, that'll give you 2048 threads on the device. So in terms of terminology, and we'll come back to this when we talk about CUDA versus OpenCL, we have an SMX on NVIDIA, and that translates to a compute unit on AMD devices. On NVIDIA, you have the hardware scheduler. On the AMD devices, you have a asynchronous compute unit. And some of these terms change over different generations, but in general, these are the general ones. CUDA cores are stream multiprocessors on AMD. Warps on NVIDIA are wavefronts on AMD. And again, as I said, there's always caveats. So on Kepler, so you have 4 warp schedulers. You can, again, enabling 4 warps to be issued and executed at the same time. So you can actually have a total of 2048 threads. Whoops, I went the wrong direction there. Sorry about that. So NVIDIA's NVLink, so something introduced in Volta. So as we move forward in different generations, we're responding to the needs of emerging workloads. NVLink is definitely a step on the way toward enabling multi-GPU workloads, particularly things like deep neural network training, where we need multiple devices with multiple batches, where we can start to interconnect these. The DGX class of systems developed by NVIDIA, they basically have started to leverage this technology, and then we have 3 different generations of NVLink so far. The most recent NVIDIA GPU has, the A100 provides 12 links for total of, for NVLink 3, 600 gigabits per second. So that's a lot of bandwidth. Then in terms of NVLink, we can build switches. So NVIDIA provides an NV switch device, which has 18 ports and has a cross-sectional bandwidth of 900 gigabytes per second. So again, some really nice features here in terms of getting some scalability. So now we can have communication not just between the CPU and the GPU, but when we want to go to GPU, we no longer have to go back through the CPU. We can go directly through NVLink, and then again, scaling this out to NV switches. To further support multi-GPU, NVIDIA came out with a collective communication library. So if within MPI, you probably are familiar with doing gathers, reductions, and scatter operations and broadcast operations. Well, now we are supporting them on GPUs, where you can actually do multi-GPU and multi-node, and it's optimized to work with NVLink. There's also support from Mellanox to actually do some of these reductions and operations in the fabric. And that's, if you read some of the most recent high-performance computing work, there's some very interesting ways to actually reduce these collective communication overhead, leveraging the nickel libraries. So on the other side, AMD's has the Infinity Fabric. So so again, this is their interconnect, and how we're gonna get scalability. So it builds on the PCIe 4 interconnect standard. supports interconnects between CPUs, GPUs, and also adds into the fabric NVMe, so a non-volatile storage. So now I can start to have, some storage in the network of CPUs and GPUs, so I can come up with new configurations. This is an area of research I'm actively working on. Where you can have up to 128 lanes of PCIe 4 connectivity, so greater than 4 terabytes per second of aggregate bandwidth. And what's really, really interesting is this is starting to provide support for memory coherency between CPUs and GPUs. So again, this goes beyond some of the current support. NVIDIA's got forms of shared memory, but this is actually taking it to the next level as well. AMD, similarly to Nickel, has RICL, which again is another collective communication library for supporting multi-GPU and multi-node collective operations, supports GPU to GPU, again, your typical gather, scatter operations, and optimized to work with PCIe 4. So, and this fits into the AMD, where their communication library fabrics. We'll be talking about this stack a little bit later on when we cover HIP and ROCm, which is the programming model that is supported today on AMD systems. Okay, a little bit about the Cuda Memory model. Just checking my time here. We're doing well. I think, what, I'm going to stop right here before I jump into, so the Cuda Memory model takes us a little bit into Cuda programming. And so with that, I'm going to just stop and take some questions. I see. So let's start. I see I have a number of questions, so I'm going to try to answer these. So, can GPUs become independent of the host? One nice features about the FPGA is, at least in principle, is it can have a soft core inside. Yes, well, again, with providing the ability to have to launch work on the GPU that then can call kernels dynamically, it can actually generate work for itself. If you look at what AMD has done, they actually have the ability to, through the HSA specification, they have the ability to launch work from the GPU back on the CPU. So if you, so the HSA standards actually support that. So yes, is it a soft core? No, it's not necessarily a soft core. Though GPUs, there are APUs that are out there that have both CPU and GPU with tighter integration. Right now, there's not necessarily the concept of a full soft core. It's an interesting idea. It's maybe something we'll see soon. So Dan asks, can you comment on the main difference between recent edge GPUs, NVIDIA Jetson, and server class GPUs? Sure. So a lot of the Jetson and Xavier GPUs from NVIDIA in particular basically come usually with an ARM host and some number of SMs on the device. Yes, you can run Cuda. Yes, you can run lots of applications on them, but they're designed to be power efficient. They're designed for a different class of workloads in terms of they're not going to be the workhorse that you have with, say, a V100. Why? Well, mainly because they have a smaller number of SMs, so they're somewhat underpowered in that sense. But they can be on board. I can tell you that Jetsons and Xaviers are really in a lot of autonomous driving applications and in robotics, so heavily used in that domain. So they're more about power efficiency. They're more, they're actually pretty good at doing what I'll call embedded applications versus server class or more general purpose across a broader swath of applications. Josie asks, which are your perspectives about the future of the architecture of GPUs? Well, that's a topic for tomorrow. I will say that I've always thought that you know, the GPU, it's you know, it's an SPMD model where you know, you take a thread and you replicate it across cores, and you run somewhat in lockstep, and that gives you some benefits, but it's also restrictive. Being able to break up and do that in finer granularities than, say, warps and wavefronts could give you some benefits, and there's some support for that. But I think there's a lot of, in terms of the architecture of the GPU, I think there's a lot more that can do, you know, memory is still a major bottleneck. I think there's things that you can do in the data path. I'll say things, dynamic compression. Or doing things on the memory side. So smart memory. So instead of, offloading to memory operations, similar to what you see with what NVIDIA does with doing reductions in network fabrics, leveraging the GPU's memory to do those operations in the memory versus bringing that into the cores. And so I think there's things that will change in the future in terms of how to do that. And we're starting to see that with accelerators in general. You know, GPUs are under a lot of pressure from the accelerator community because the accelerators are really, and the accelerator community is really focused on, you know, inference and training and doing that very fast and very well. So, you know, you're seeing some very interesting models there. So I think that's a great question, and there's definitely a lot of room for more work in this area. So let's see. I try to answer these in the order that I see them. Shabam asks, can GPUs become independent of the host? Yes. Well, again, I think I answered that before. Yeah. Okay. I answered that one already. So Naveen asks, do special function units, SFUs, what do special function units? So these are used for things like transcendentals and things that are more complicated, and they get implemented within that unit. So can they be used to carry out some common functions such as sigmoid and tanh? I believe tanh, I have to go back and see. I don't use the special function unit that often myself, so I'd have to go back and look at the support, but transcendentals in general. So let's see, Dan asks, can you comment on the main difference between, we already covered that one, so let me see. I answered that. And then going down, Thomas asks, what are your thoughts on the SIMD CPUs? Neon, AVX, SSE versus GPUs. I actually do some work on AVX right now, so that's an interesting question. So CPUs have SIMD units. There's a lot of potential for acceleration with SIMD units. And you should always use the CPU for, you know, if it's there, use it. Otherwise, it's just, it's maybe idle, but it's still leaking some current. So, you know, use it or lose it. So I'm a big fan of leveraging the SIMD units on the CPU side. One of the areas that I'm currently working on is looking at how to leverage some of the, you know, some of these units. The fact that you have a CPU that can actually do things like run a jitter and actually do optimization of the code that runs on the vector units. That provides a whole window of opportunity for all kinds of optimization. So we're doing some work in that area. So very good question. Okay, let's see, get my pointer back. So I'm going to dismiss that question. So I answered that question. Willie asks, no comparison with ARM Mali GPUs? What about SGEM per watt, for instance? I don't have that data, I'm sorry. I probably should, but most of my work is targeted at the higher end of the GPU spectrum. Mali GPUs is a great target. It's and again, ARM has very competitive products out there, or architectures out there, and there's implementations. So it's something we should study more, but I personally have not studied it. So sorry, I can't answer more on that in terms of SGEM per watt, for instance. Davia asks, when multiple threads are spawned on GPUs, aren't there overheads due to synchronization? Well, so synchronization is under, as we'll find out very shortly, under programmer control. So that's, that's sort of our, what we have to watch out for is, not creating race conditions. So we want to do as much of that. So if we're doing a lot of SIMD operations, like hundreds of thousands, the GPU works really well. When we have to do finer grained things and their synchronization, think about the CPU. Okay, it might be a better place to actually do that kind of work. Chuck asks, can you talk about how scheduling of kernels works across SMs, warps and threads? So basically, there's the so it's done in hardware, and basically the kernels, or sorry, the warps or the wavefronts basically have resources that they need. If those resources are available, they're runnable. And I think, so basically it does try to do them on, the details of the scheduling algorithm. You'd have to talk to the vendors to hear the actual details. But in general, you can think of it as round robin. It's and again, but they have to be runnable. Okay. Thomas, charge equilibrium. I'm not sure what that question is about. So Shabam asks another question. What is the primary difference between SIMD and vector processing? It's very similar. And again, you can use similar terminology. I've seen a higher interest in the RISC-V community towards vector extensions than SIMD. So, SIMD is sort of a simple way of executing parallel threads. Vector is within a single thread, you have a unit that will run on multiple data. You can use both of those. So, let's see. Nicholas asks, is special function unit the same as fixed functions? Saw on a GPU architectural marketing slide. Not sure. Not sure what that fixed function, it could be the same. I think it is. Kim asks, what is the difference between a DSP and a GPU? Well, DSPs have somewhat of fixed pipelines. They're designed a lot around, I've worked a lot on DSPs in my past life. And they tend to have good multiply accumulate pipeline support. They can be they're more specialized in terms of the support for a particular class of workload. GPUs, well, it keeps changing. We're actually customizing GPUs for deep learning now, like I've never seen before, which surprised me a little bit, but not too much, just because of the size of the market there, at least for now. So a GPU is a little less programmable, I'll say, in that sense. You typically, your DSPs many times are programmed in assembly, and GPUs tend to be at a higher level of abstraction. So in that sense, there are some major differences. Okay, I think I answered all the questions that I see. Let's see. I answered that. I answered that. So let's take a 5-minute break, and then probably the top of the let's take a 3-minute break. A little bit after the top of the hour, one after, we'll begin again. Okay. So yeah, while we're waiting, I just want to thank everybody for their great questions. Those were all good questions, so appreciate it. Okay, I think we'll continue. So let's talk about the Cuda memory model. So how are we going to actually program this device? Now we have this nice parallel fabric. We have our workloads. How do we map those workloads to the hardware? Well, first thing we start with, again, it's very hierarchical. It's very nice the way the architecture is designed. It's very nice that the way the programming languages are designed are also to exploit that same type of hierarchy. That hierarchy maps well to many of the programming structures that we use in high-level languages, such as loops, nested loops. So again, we're going to develop a kernel. So this is the unit of work that's launched by the host. The host is the CPU. Again, you're going to have, very similar to a C function or C++ function. It gets executed on the device, the GPU. So we use these terms host and device to mean CPU, GPU. So just be comfortable with that. All threads execute the same code in the kernel. So very straightforward model. It's, we call it SPMD. So, single process, multiple data. So basically each thread's going to be chunking on the same data or different data. So from a kernel, we move down to a grid. And this is a 1D or 2D organization of a block that has different dimensions. That's what's we're going to send the grid to the device. The grid is further broken down into a block. The block is assigned to an SM. So depending on how many SMs you have that many blocks. And that's a 1D, 2D, or 3D organization. And then within the block, you have a number of threads. So why is it important to understand the memory model on a GPU? Well, I will say that memory is probably the key ingredient for getting performance out of a GPU. And if you mess that up, you might as well be running on a CPU. Because you're going to have you're going to have thousands of cores sitting there and just, waiting for the compute the compute is just sitting there waiting for memory to respond. And so you'll have long queues, get very poor performance. So you need to structure your memory pattern. We're going to talk a little bit about that to enable you to improve performance. And again, this class is only 2 2-hour sessions. I really don't have the time to give you CUDA optimization tricks, and we actually teach my graduate students. By the way, I should recognize all of these slides. Many of them were developed by my graduate students over the years because we actually teach on campus a CUDA class every semester. So you can structure the memory pattern, so you can change how you traverse various data structures so that you can improve performance significantly. You can choose where those data structures get mapped in the memory hierarchy. You have to consider the pressure that you're putting on load store units so that you can best utilize the compute resources that are available. So in terms of locality, most GPU applications exhibit a very regular access patterns. And irregular patterns are really going to be challenging for the GPU. Things like sparsity, things like, complex graphs. These are harder to run on the GPU. They can still run on the GPU and get good performance, but you don't get the same kind of scalability that you get from doing things that have high spatial locality. So what do we mean by locality? There's temporal locality and spatial locality. So temporal locality is I reference something now, I'll reference in the near future. Spatial locality, I address something at address A, and then A+1, A+2, A+3 will be referenced in the near future. So really we're going to focus on spatial locality. Spatial locality is, temporal locality is more of a function of the application or the data structures we're using. Spatial locality, again, we have some options in terms of how we can exploit spatial locality and get the most out of it. So in terms of the Cuda memory model, we have different memories on the GPU. Excuse me one second. There we go. So we have registers. Registers are the fastest and closest resource, and we have to manage them carefully. We have shared memory, we have local memory, we have constant memory, we have texture memory, and we have global memory. And something texture memory, yeah, a lot of the terminology is a leftover from graphics. So, and still remember, a majority of these devices have very similar architectures that are still used for rendering your graphics every day. Excuse me. So registers are the fastest memory on the device. Variables can be automatically assigned to registers. Some arrays can be declared as being register-based if you can deduce their size at compile time, and that size is constant and doesn't change. So again, here are our registers, close to our thread units. What happens if we exceed register, the limits in the hardware? We get spills, and so we're going to spill. These spills impact performance because the data is spilled to local memory, and local memory is in device memory. So that's expensive in terms of the cost in terms of performance. So local memory, variables that don't fit in registers are stored in local memory. Again, any arrays whose indices cannot be determined at compile time are stored there. Large local arrays that consume too much register space, and anything that spills that doesn't fit in the register file. Shared memory, this is a great feature that basically gives you, so that think of for those of you that have worked in the embedded space, you probably worked with devices that had scratch pads. So this is a form of scratch pad. The programmer has control of it by using the shared attribute. It's on chip, so it has much higher bandwidth than global memory. Global memory is basically, the last level of the memory hierarchy. So it's much lower latency than the shared memory is, but it's much smaller than than global memory. So you can assign the amount of memory that you need, and shared memory in the L1 use the same physical space. And this is on Kepler for the 64K on-chip scratch pad memory. And again, that's going to differ based on each architecture as you move forward through the NVIDIA family. But the basic concept's still there of shared memory. So shared memory, you can declare it in the kernel, works at a block level granularity, so threads in a block can access the same shared memory space. When a block is done executing, the shared memory will be released, and you can use a sync thread to synchronize threads in the block to avoid hazards and race conditions. So shared memory is probably the easiest way to get performance. So basically, when you declare something as shared, so my block here will be shared, it will be mapped to shared memory. When it actually gets allocated and managed, basically that's going to give me some nice performance. So constant memory, again, I will use a attribute in my kernel code and my Cuda code. So it's read-only, it resides in device memory. It has its own separate cache. It has the constant cache. Constant memory has to be declared on a global scope outside of the kernel. And it's for, in this particular, for Kepler, it's 64K for all compute capabilities. So, so the host needs to initialize it in terms of the constant memory. And then it works really well when all the warps access the same memory address, but better not to use it if they're, if a warp accesses different memory addresses, and because again, it's not in shared memory, it's going to be much further away. Texture memory, again, so texture sounds like something, it's a read-only memory, and there's a texture cache on a per SM basis. It belongs to the scope of global memory, but it can only be accessed through the dedicated read-only cache, and it works very well if you're doing things on images, so where you have a 2D image, so it'll work quite efficiently for mapping. So constant memory, whoops, I think I went the wrong way, there you go. Global memory, so resides in device memory. Again, so the device memory is where the host communicates with the device, moves things back and forth. So resides in, so it has global scope, so accessible all across the device. It's the largest memory on the GPU. It also has the longest latency. So how can we maximize the usage of this? Well, we have to be you know, if we can use shared memory better, we will limit the amount of time that we're actually in global memory. So GPU has caches. So there's 4 types: L1, L2, read-only constant, and read-only texture. So again, and so the L1 is there's 1 per SM, and the L2 is shared across all SMs. So L1 and L2 store data, and again, these will change slightly, not necessarily too much, but the first 2 are, I think, common across all GPUs. But L1s and L2s store data for local and global memory, including register spills. The GPUs can be configured that just reads are cached in L1 and L2, or just L2, and memory store operations cannot be cached. So in terms of GPU memories, you have these 3 qualifiers, you know, in terms of for a particular variable, and this is where it gets mapped. This is its scope within the program, and this is its lifetime. So again, it will get reclaimed, and so you can actually manage things this way. Let's talk we'll talk briefly about GPU synchronization. So, you know, many applications require different types of synchronization between blocks, you know, within a block, between 2 blocks, and between the CPU and the GPU for concurrent execution. So how do we manage this? So intra-block, within a block, we have sync threads. So all the threads have to reach this point, ensures that threads are all blocked until everybody reaches that point. And so it basically implies a memory fence that as well. So works quite well. What is a memory fence? So you can have different types of fences. So you can have a thread fence block, which basically doesn't synchronize threads. But basically stalls the current thread until all writes by this thread get to shared memory or global memory or visible by the other thread. So it's a form of synchronization for a single thread. It's reads and writes. So it's, and this can be used for supporting consistency models as well. A thread fence basically does a little bit more. So it acts as a thread fence block and a global memory write ordering. So it basically gets the global memory writes in a particular order. And again, it ensures that the device can see the writes to global memory in a particular order before you know, the threads write anything to global memory after the call. So it's a ways of getting reads and writes seen by other threads. So so beyond you know, how do we get inter-block synchronization? There's no explicit way of doing this on a GPU, at least for Kepler. For later architectures, there's more support, and again, more support for atomics. So, and I'm not going to cover that in this particular presentation, though we can talk about that offline if you'd like. So, the way you do this between interblock is you're going to basically, you can do atomic operations in global memory, but that should be avoided. It's very costly. So you'll have to go back to the CPU and do the synchronization back to the CPU and copy data back and forth between the CPU. How can we avoid race conditions on GPUs? You know, it happens where, you know, depending on the ordering, it attempts to perform 2 or more operations at the same time. So how do we get some ordering? So we can do atomic instructions. There's special hardware instructions that perform operations on 1 or more memory locations atomically, so indivisible. So this can be done for locking. This can be done for other operations where you have shared data structures. An atomic operation can either succeed or fail in its entirety. So, you know, if it tries to do the atomic operation, someone else has an atomic operation underway, so it has whatever you're trying to do locked. So it can be done for collaboration. So maybe you're updating a sort or a histogram. and you have a partial result that you want to basically provide. You may be doing it for synchronization, which again has counters, locks, or flags. You know, Cuda provides atomic functions on shared memory and global memory. So they're at the instruction level. So you basically have, you know, in Cuda, you'll have an atomic add. So at the PTX level, you can do atomics as well. PTX is basically the intermediate representation of the actual Cuda code. SAS is the instructions at the lowest level that run on the GPU. So you can have arithmetic functions bitwise. And again, here are just some examples on Fermi, Kepler, and Maxwell. Okay, so how do we use memory properly? So Cuda memory model, okay, so each thread can read and write per thread registers, can read write per thread local memory, can read write per block shared memory, can do read write per grid global memory, can read only per grid constant memory. So per grid means the whole device, okay? So again, it talks about the scope, talks about how reads and writes are managed. So so why is shared memory so fast? Well, besides it being close, it basically comes in memory banks. So it's divided into banks, so we can get some very nice performance if we're able to have our threads accessing individual banks and not conflicting for the same bank. If we do conflict for the same bank, as we're showing down here, these get sequentialized. So, so bank conflicts in shared memory. So basically, we want to avoid bank conflicts if we can. Each bank can service one address per cycle. It can also do broadcasting as well, but we'll talk about that in a second, where things can be coalesced. So access to shared memory is fast unless two instructions in a warp access different banks. And again, when they all are in the same bank, and we can do a broadcast, which is very beneficial. So very nice and aligned. These can be, again, very efficient. Again, non-sequential. It's going to give us trouble. When accessing a single address, this basically becomes a broadcast back to all those threads. This is an example of coalescing, very, very effective on GPUs. So coalesced memory containing combines multiple memory accesses into a single memory transaction. And particularly on Kepler, every success of 128 bytes, so that's either 32 single precision words, or depending on what your data structure are, 64 double, can be accessed by a warp, 32 consecutive threads in a single memory transaction. So basically, this will have, everything can be done in just one single memory transaction, very, very efficient, and then the results broadcast to the threads. Or actually, they can be presented to the threads, that one block. So, but, things that cause uncoalesced loads are, when memory accesses are not sequential, when memory accesses are sparse, or there's misaligned memory accesses. So those are all problematic on a GPU. Okay, so next I'm going to just sort of summarize some of the big ideas around parallel programming software, where we've been, where we're going, cover a little bit of OpenCL. So hardware vendors have tried to roll their own programming languages for GPUs. Cuda is NVIDIA's, and again, until very recently, Cuda only ran on NVIDIA GPUs. So what do you get when you do that? Well, you can, if you get a lot of people learning Cuda and that's the primary language, you can dominate the market. NVIDIA's been extremely successful doing that. AMD had CTM and Brook Plus. Those were very low-level programming, didn't really catch on. Intel CT technology, again, another approach that they were using for their GPU, didn't really catch on. Microsoft came out with C++ AMP, not that they had a GPU necessarily, but these were being supported in both NVIDIA and AMD at some point. But again, it was very vendor specific in terms of they were providing that support. Instead, there's been open software parallelization technology that's been produced supporting heterogeneous devices. Kronos is OpenCL, the HSA work, and then now ROCm and HIP, which is, again, we're going to talk about a little bit more later. OpenAC was a really, I liked OpenAC. That was a, OpenACC was directive based and basically could support x86 power CPUs, so the power architecture, NVIDIA GPUs, and Xeon Knights Landing. So, you know, Xeon Phi. So in general, you know, the GPU model, basically you have host and device code. So the host code runs on the CPU, the device runs on the GPU. Again, we're going to talk a lot about Cuda here for a little bit. This is the highest performance programming framework for NVIDIA GPUs, and it's very similar to C and C++. But you have to just work on the mapping between you know, your programming structures and the underlying hardware. So, you know, Cuda is you know, is a standard ANSI C-like language. It has a set of APIs for managing devices, memory, synchronization, and other features. Again, oops, I went the wrong way again. So, so basically the Cuda API offers two levels. There's the driver API, which is sort of a low-level API offering better control over the GPU, or the Cuda runtime API. You can see how this sits in a hierarchy implemented on top of the driver API. So in terms of, you know, if I want to do something in C code that I would run on the CPU, you know, I have something that's, you know, done that's using INJ. Here I'm going to, in my Cuda code, I'm going to map this to threads. And I'm going to, you know, map the I and J to block indices and thread indices. And then the code here will use I and J. And so whatever I was doing in my C code on my CPU, I can move very easily to that portion of it to the Cuda code that will actually do the work on the GPU. So some concepts. We have host and we have device. Okay, you're going to execute still a main program on the CPU. You're going to set up the kernel launch. You're going to launch the kernel. You're going to read the results from the CPU, and you're going to execute other work on the CPU. The GPU basically is taking whatever kernel you passed it, whatever data you passed it, and then chumps away on it, signals when done. It can also launch its own child kernels as needed. So Cuda kernels, they're, you know, basically thinking of them as, you know, we're looking for data parallelism. They're callable from the host and executed on the device, and it will run many threads in parallel. We have the Cuda compiler, which is NVCC. So the compiler first separates the device code from the host code, even though we write it as one, and basically compiles the whole mess, and then we can run it. So the kernel code runs on the GPU. It's executed by a GPU thread. It's very simple. We're going to copy data from the CPU to the GPU. We're going to invoke kernels, and then we're going to copy things back. And we have API calls for doing each one of these. And so, you know, well documented, easy to use. So I'll show you a simple example. So we allocate space. We're going to do a Cuda malloc, just like we would do malloc on a CPU. We have we transfer data with a Cuda mem copy, and we say what kind of copy, whether it's host to device, if we're sending data from the host to the GPU, or if it's from the device to the host, from the GPU to the CPU. We invoke kernels to operate over the GPU. It's an asynchronous call. So let's assume we were going to add two vectors together, A and B, and produce C. How would we distribute the number of threads? So we would basically, on our grid, describe how we're going to map this to blocks, and then within blocks, how we're going to map this to threads. So how should we distribute the number of threads? And what happens if we're changing between a matrix and a vector? Would we need some, and let's say we're doing, in terms of computing C sub I, do we, for this very simple add operation, we really don't need to do a lot of complex synchronization, but we may. So invoke kernels that operate over the GPU asynchronously. We're going to organize threads. We're going to have the number of threads per block. Again, we're going to describe this with a thread index and a block dimension index. We're going to have the blocks that are in a grid. So again, very hierarchical, and we're going to map the data structures to those actual hardware units. So how should we define thread blocks and grid size parameters? We use basically the DIM3 data type, which basically provides us with a way of describing using 1, 2, or 3 parameters. So it's an integer vector type that's used to pass the grid and block dimensions to a kernel. It's defined within vector types.h. You basically have variable x, y, and z, and can take 1, 2, or 3. For instance, I can have a 1D block, 2D block, or 3D block described. The invocation is, so when I call a kernel to start, I'm going to have the kernel name, and then I'm going to specify the grid parameter and the block parameter, and then argument list. So the grid times the block is the total number of threads that are going to be launched for the kernel. So picking the right grid and block size is really key to getting the best performance. And the compute capability for whatever version of CUDA that you're running with and what device you're running with the driver support will limit the number of threads and the max size of the blocks and the number of registers that get allocated per block and the amount of shared memory consumed by a block. So those are some of the details that you really have to learn about when you actually do CUDA programming. So you'll also may need to test out different configurations of block sizes to get the best performance. And so some of this is trial and error. You can use, the occupancy calculators that NVIDIA provides you with to see what you will actually get in terms of getting throughput. So again, I would pass, 4K and 256 as my argument parameters for my grid and my block. So I get my grid dimension of 4096, and that will tell me how many blocks I have. So I can index each one of the blocks. And then within each block, I have a thread ID. I have 256 threads per block. And so to get to any index of an individual thread, I have the block index times the block dimension plus the thread index offset. So I can get to any particular thread. So how many threads in total? Well, basically 1 million. So lots of threads. Why do we want a lot of threads? We want a lot of threads because we're going to be issuing these warps that basically we're going to be and we're going to be able to swap warps in and out whenever they do loads. It's generally going to be a long latency operation. It may be, and if it is, we're going to swap that thread, that warp out, and bring in warps are the schedulable unit on the GPU. So we'll swap them in and out. So groups of threads. So in terms of writing kernels, we talked about scope and other things. So global and device are two qualifiers that we use commonly. So this is, it's executed on the device and callable from the host only, in terms of having for the kernel name. And then the device qualifier is called from the device. So we have to, where it's called from. So again, there's some restrictions on using these that you have to pay attention to. So let's take a matrix multiply. So here we have A, B, and C. This is the C version of it. Again, we're gonna, we initialize A and B here, and we're basically going to time this. And so here we have the A times B, putting it into a sum, and then we do the reduction here into C, which we call test. And so again, we're gonna time this and see how fast it is, and compare it to doing the same thing with doing it with Cuda. So now here's my host program. Looks very similar. So I'm going to do matrix multiply, but I'm going to do Cuda Malix here. And again, I'm going to define some variables, device A, device B, device C. Whoops, sorry. And then I'm going to do a Cuda mem copy from the host to the device. So I'm transferring from the CPU to the GPU. I'm going to send A and B. I'm then going to set the dimensions of the grid. And then I'm going to, and again, I do some computations here to get so this is the block dimensions and the grid dimensions. And then I launch the kernel with the grid and block dimensions that I've computed based on the size of my, of how big my matrices are, and adjusting for that. I do the kernel call, and then asynchronously I do the Cuda mem copy back from the CPU to the GPU, and then I free the memory that I allocated before. So here's the actual kernel call of the Cuda kernel code. Again, all of that was the host code. So this is global, and basically doing the matrix mult kernel that gets called, and I have the thread ID, gets the block index, the block dimension, the thread index, and then I'm gonna do this across rows and columns and do the multiply, do this iteratively, and then, and again, actually do the reduction. So I compile it and I run it. And if I compare the sequential time, this is on, I think on the K40, I got I'm running 5 times faster, or a 20% reduction in execute, or sorry, 20% of the execution time that it took before. So some significant speed up. And that's before I do any tuning. Okay, I've covered Cuda. I've covered enough to get you started, and you could go off in tomorrow and probably try some simple kernels. You could try that kernel and you get started. If you're going to be working on GPUs, I encourage you to take a full Cuda class or OpenCL class, or a ROCm class, HIP ROCm or HCC. Next, I'm going to talk about OpenCL. These are actually 3 books that I co-authored with various people over the years on OpenCL. So we've worked on OpenCL in my group quite a bit. This was a really compelling, OpenCL is very compelling in the sense that it's designed for heterogeneous devices, trying to provide for execution on CPUs, GPUs, and other processors as well. FPGAs, we've done work on FPGAs with OpenCL. The idea is you'd have portable, accelerated code. But I will also add one caveat that performance is not portable in itself. You generally have to optimize for each particular platform to get the best performance. So OpenCL has 4 different models that define the execution: the platform model, the execution model, the memory model, and the programming model. I'll cover these very quickly in this presentation. So in the platform model, or also called the host device model. This basically describes how I'm going to have a host connected to some sort of device. Here I have, and again, I'm describing this as I have a compute device. It has compute units, and within the compute units, I have processing elements. Very similar to what NVIDIA has in terms of their organization. So a device is divided into one or more compute units, and again, compute units getting down to processing elements. So we talk about a context. So when we build computation in OpenCL, we're going to build this context. We're going to set up resources. We're going to set up our data. We're going to set up execution pipes, queues, and then we're going to set all these things up, define them, and then say go, and the context will fire. So to manage programs, you have devices, program objects, kernels, memory objects, command queues. Okay. So when you create a context, you again, because OpenCL allows you to work across different devices, you can build a context to have different classes of devices. You start with an empty context, and then you associate devices with that context. So you have a create context. It creates the context with a list of devices. You have other properties and things you can specify within that API. This is OpenCL syntax. Command queues are mechanisms for the host to request that a device perform an action. So basically, think of them as sort of pipelines between, or interconnects, virtual interconnects. And you can use this for transferring memory, issuing kernels to start, all kinds of things. Commands can be synchronous or asynchronous, so it's very flexible. Cuda is much more restrictive and has a certain protocols that are baked in. Here you have more programmability. Commands can execute in order or out of order, so that's, again, that adds to some more flexibility, but also adds to more work that the programmer has to do. So you're going to build command queues that are basically where I'm going to send the commands to these devices within my context. I have memory objects. Just checking my time. I have memory objects that are OpenCL objects that can be moved on and off of the device. Objects can be either buffers or images. So buffers are contiguous chunks of memory. They're stored sequentially. It can be accessed directly. They can be arrays, pointers, structs, whatever you like. And they're readable or writable, or both. Images they're opaque 2D, 3D. They can only be accessed with a read image and write image, but they can't be both read and written in a kernel. So I can associate different memory objects to this context. And again, so you can think of it as I'm sort of setting up this container that has devices, queues, data. And so I have APIs for creating buffers. This is just giving you an example of that. Images, doing it for images is a little bit more complex. And then I transfer data, so I can enqueue the data with either a read or write to the device. So writing is basically the host to the device. Reading is from the device to the host. And again, and I have the ability on a write, both initializes the memory object with data and places it on the device. So then I can do transferring of data. So memory objects are transferred, so I can read and write them. Then I have programs in kernels, basically the collection of OpenCL kernels that can be compiled and then get associated with a context. So in terms of how computation works on OpenCL versus Cuda, I have thread, blocks, and grids. OpenCL, I have work item, work group, and then an index space or an ND range. Very similar, same hierarchical structure. It's fairly straightforward to take Cuda code and move it to OpenCL and vice versa. So, and again, so Cuda terminology versus OpenCL. This is taken off, I think, AMD page. Grid dimension, get number of groups. So here you have APIs for 3 things. Through your thread index is, get local ID. There's no, basically, I can get the global ID where a thread is in the global space. I can the size of the global space. I can compute these on NVIDIA CUDA, but I don't have an API or a direct variable for managing that directly. So in terms of, I can have global, constant, local, and private. So basically very similar to what CUDA has. So, and so global is global, constant is constant, shared is local, and local is private. So again, different terminology, it gets confusing. So working between the two can be confusing from time to time. So you have address space identifiers, global, constant, local, private, read-only, write-only, used for images. Kernel arguments are memory objects that have to be global, local, or constant. Okay. So again, just the terminology, the keywords. So this is what you get with OpenCL. You get this concept of a context that allows you to describe how you're going to bring together devices, bring together programs, kernels, memory objects, command queues, and then you compile the code, create data arguments, and send it to execution. So, and again, OpenCL is still alive and well. There's variants. There's a lot of work, follow-on work that's being done related to HSA and also SYCL. There's a really popular workshop that we hosted at Northeastern recently, the IWOCL workshop, the International Workshop on OpenCL, that you can go learn more about. So again, the CUDA OpenCL versus CUDA runtime. So with OpenCL, you have to do a lot more work, but you have a lot more flexibility. I have to get the platform ID, the device IDs, create the context. There's no such thing as a context in CUDA. Creating command queues, creating buffers. I have a CUDA malloc over here. Again, in queuing, I have a CUDA mem copy. So doing reads and writes, creating the program with source, building it. Again, it's a lot simpler in CUDA, but I have a lot more control over in OpenCL. So I think that was a good contrast between the two, and you see they have, CUDA's popular because it's in many ways simpler. OpenCL for the embedded domain is quite popular, and that programmability is quite attractive to work across different devices in an embedded solution. So next, I'm going to briefly talk about ROCm and HIP. These are the emerging framework that's coming out of AMD. So ROCm is the Radeon Open Compute Platform, targeting current generation and next generation AMD platforms. It leverages the heterogeneous system architecture runtime that was developed. And that's a very rich runtime that provides for a lot better usage of both CPU and GPU in terms of integration. It's programming language independent to a certain degree. It targets both HPC and machine learning environments, so it's fairly generic in that sense. It can be combined with HIP, which basically allows you to support execution on AMD and NVIDIA GPUs as well as CPUs. So ROCm has a number of modules, and includes supported GPUs, device drivers, runtime system, programming frameworks, libraries, application frameworks, and development management tools. Let me cover these briefly. So in terms of supported GPUs, Radeon GPUs are supported, and also the Radeon Instinct GPUs. So these are some of the more recent GPUs out of AMD that are supported within the ROCm runtime. So this is where you can actually run the ROCm runtime. In terms of device drivers, it basically, the ROCm GPU driver, it's supported in Ubuntu and Red Hat, as well as CentOS, and also can support trunk driver interface communications. So the HSA runtime is a low-level device manipulation, so it allows for better interoperability from the layers above. So it's very rich in that sense. We actually worked on the HSA Foundation for a number of years and did a lot of both standards work and as well as evaluation of HSA and HSA compliant systems. So in terms of programming frameworks, HIP is supported, OpenCL, though that's being deprecated, and HCC, C++. So in terms of library support, we have MIOpen, which is basically machine intelligence. Basically, a lot of the machine learning workloads are there. So the OpenGem, the OpenBLAST, the HipBLAST, RockSparse, HipSparse, RockFFT, RockRAND, and RICL are all supported in terms of the ROCm runtime. Application frameworks, they have TensorFlow, Caffe, PyTorch, and this list is just rapidly growing. So this is just some of them. So I know they have a large number of HPC applications. Our group is actually contributing to those as well. In terms of developer tools, there's the assembler, they have an assembler and a disassembler, the Rock Profiler, the Rock Tracer, the Rock Debug Agent, and the ROCm SMI, and there's support for Docker as well. So in terms of application frame, whoops, I'm going the wrong way again. So what's different between HIP and Cuda? So HIP is the most commonly used development language for the ROCm runtime. Both HIP and Cuda are dialects of C++, so there's a lot of similarities if you looked at HIP. For NVIDIA platform, HIP requires Cuda 6 and beyond, which provides for unified memory, because HIP is going to start to view the memory system as a unified system. Allows the user to run the same code on both AMD and NVIDIA systems. And performance when you run HIP on Cuda is, it runs very similar to how Cuda runs. A lot of applications have been run and measured, and there's about a 5% overhead for HIPified Cuda. Okay, so let's see, we're near the top of the hour, so I'm going to summarize here and then take questions. So what have we talked about today? We've learned about the reasons why GPUs have become popular accelerators. We saw the limits of CPUs. We saw the growth and the capabilities of GPUs and we talked about the applications that are running on these platforms today. We learned about the basics of the GPU's architecture, how it differs from the CPU. We've learned a little bit about how it's organized hierarchically and how it maps nested loop structures and matrices and vectors very nicely to this hierarchical machine architecture. We've learned about different options available for programming a GPU. And again, we focused mainly on Cuda, but we talked about OpenCL, and we talked about HIP and ROCm as well, and learned about those emerging runtimes. So both NVIDIA and AMD are firmly committed to growing the role of GPUs in HPC and machine learning. I think they have very interesting products coming out. They're innovators, both of them. And we're going to talk more about other types of innovations that are being developed in our next session. So in tomorrow's talk, we're going to basically go over GPU simulators. So how do you get started being involved in this ecosystem of GPU research? Learn how to use a simulator. We're going to basically take you through the basics of one particular simulator that's actually being developed by a community of researchers, both in, that it's an international community of developers, but was started within my group. We'll also talk about GPU research directions that are quite compelling in terms of multi-GPU and scalability. Then we'll go into related topics on GPU reliability and GPU security. So these are two areas where now the GPU is becoming a first-class citizen in the data center, in high performance, in machine learning. We need to have a device that is reliable, that doesn't leak secrets. And we also need a device that can run for, has the same kind of in class of reliability that we expect on a CPU. So again, look forward to talking to you tomorrow. Now I'm going to pause, and I see I already have 10 questions. So with that, I'll start working on the questions from the top. Dan asks, is global memory the same as host RAM? Well, on a discrete device, no. Host RAM is on the CPU. It's on the it's on the host, and it's used for the CPU. It's a separate memory that's on the physical GPU. So that's a good question. Thomas asks, since shared memory and L1 share the same space, wouldn't a cache default followed by a hit, wouldn't a cache default followed by a hit be as efficient as using shared memory? No, because you have, so with a cache, you are, if you don't have certain locality, the cache will be replaced, what's in the cache, whereas in shared memory, you have control. It's a scratch pad. So sometimes you want that programmability and keep things local that you're going to use time and time again. You may not get that if you use the L1 cache, use it as L1 cache. So there's differences in terms of utility. Things that I am going to continually refer to and want to make sure that are always there, I may map to shared memory. Things where the L1 cache can be, we'll get some, I'll get some reuse, but maybe only near-term reuse, I'll let to be cached. And so I'll choose, what data structures to map to what areas. And again, I'll do this data structure by data structure. But good question. Are caches coherent? They're not across different caches, no. So that's a good question. Our access is, within, so there is sharing across, the L1 cache across the SM, but no, they're not coherent. At least they're not coherent yet. They're about to become coherent, and that's what part of tomorrow's talk is about. So that's a great question. Azil asks, what do you think about L2 cache residency controls in the A100? Does the trend go towards more software-controlled memory structures? So I believe that allows you to do some pinning in L2. And again, I haven't looked at all the details of that because the A100 just came out recently. So, adding more work for the programmer to do to get performance is going in the wrong direction, in my opinion. I think we need to have hardware that can figure things out to do what you would do, what the programmer should have done. And that's my approach. Sometimes you still want that configurability, as we just talked about with shared memory. So Software control just adds burden to the programmer. It keeps programmers employed to get the highest performance, but it also adds to the burden of everyone else. So again, very good question. Alejandro, as one of the main disadvantages of using GPUs for real-time applications is that the vendors only support general purpose operating systems. The best we can do is use Linux with preempt RT patches. Do you know about projects using GPUs from bare metal applications or real-time operating systems? I would refer you to some of the work that goes on the Tegra class in terms of, are they using bare metal applications? I'm guessing that there are, in the sense that, so they're using the GPU for driver navigation. So I would look at some of the embedded GPU solutions there. Again, probably on lower end GPUs that are on portable devices, you'll also see that. So GPUs being used for robotics, I think in you know, the robotics operating systems, which are closer to bare metal applications, you know, they're probably also another place you can look for some examples. But very good question. Sergey asks, what do you think about Vulkan Compute and Spear V? So I actually think so this is a follow-on. I believe Vulkan is a little bit more toward integrated graphics as well, and Spear V, again, so, and I guess I'm not sure what the relationship there is with Sickle, but I think that's all wrapped together. I forget all the details. I haven't done a lot of work on either Vulkan or Spear V. I am familiar with it as it's associated with OpenCL, but that's a good question. I probably need to look up the answer, but I'm sure you may actually know the answer, but I don't. I know there's a vibrant community out there for Vulkan and Spear V, particularly Spear V. A lot of interest. Nicholas asks, can a conflict between a thread barrier and the internal threading mechanism that dynamically spawns threads? Can a conflict happen between a thread barrier and the internal threading mechanism that dynamically spawns threads? So this is sort of hierarchical threading. I would probably need to have a specific on what platform, because different platforms and different languages and different runtimes handle synchronization and thread barriers differently. So I think I would look at the HSA runtime for ones that's most flexible. Cuda less flexible. I guess that would be my answer. But kind of conflict and the internal threading mechanism. Not sure what you mean by the internal threading mechanism. So maybe we can take that offline. Thomas, is there a difference in execution time between dynamically allocated shared, the third argument, and a fixed sized shared? So I believe that gets allocated on the host, and then it's still just a copy to GPU memory. So, or are you thinking dynamically during kernel runtime? But you're doing it on kernel call and kernel invocation, so that's done on the host and then copied over to the device. So I don't think there's, I'm a little confused by the scenario, but maybe we can talk more about that. Okay. Is there any limitation about the number of threads which are in a block? Yes, there are the number of threads in a block. So the number of threads in a warp and the number of warps within a block. So there are limitations, yes. Can HIP programs reuse, import existing CUDA kernels somehow? So Dan asks a good question. Yes, I can HIPify CUDA kernels. So there's a HIPify that basically moves this so that you can actually run on the ROCm runtime through a translation that takes place. So yes, very good question. Yes, look up HIPify. Could you comment on the usefulness of cache coherent interconnects? For example, the new CXL interconnect for GPU. Yeah, I'm a big fan of this. I think cache coherency interconnects are the future for GPUs. We're actively working in this area, and I'll be talking more about this tomorrow. So thank you, Chuck, for the interesting question. Daniel asks, also, do GPUs support any kind of hardware prefetching, or is this mostly up to the programmer? Generally, I get confused because there's a lot of research that's looked at GPU hardware prefetching, and each microarchitecture is a little bit different. There are, to my knowledge, I don't believe they do a lot of hardware prefetching, but I could be wrong on a particular implementation of the system. So I don't know that off the top of my head. And David asks, I didn't understand, when does the CUDA OpenCL code is compiled? Is it compiled together with the host code? So you can compile it offline, or you can have it pre-compiled. And also what happens also, the driver does a final compile. So you generate sort of IR to the driver that then generates the actual binary that gets loaded on the GPU and executed. So yes, there's two different scenarios, but you're going to have host code. So that host code and device code is can be in one program, but the compiler breaks it out, and then you have two binaries, one that works on the host, one that works on the device. You can think of the device code as sending a bunch of string data to the actual device that gets stored and treated in instruction memory. So that's a good question. Okay. Daniel says, can you give any practical advice for CUDA programming on Linux? In my experience, it's very tricky to get set up and is broken quite easily by kernel upgrades. Well, so practical on CUDA programming on Linux. There's a number of good tutorials that are out there on CUDA programming, one particularly out of Wenmei Hu's group out of Illinois that that's been online for quite a while. I'm not sure how up to date it is. I know NVIDIA has also materials for education that may be useful. In terms of kernel upgrades, that I can't help you with too much. I'm not a vendor, but I feel your pain. Okay, I'll wait for a couple more minutes to see if there's any more questions, but that is our 2 hours. And I thank you for the very good questions. Sorry I couldn't answer all of them, but I don't know everything about a GPU. There's plenty of things I still have to learn. Okay, seeing that there's no further questions, I want to thank everyone. And again, we'll at the same time have our class tomorrow, and I'll be covering simulators, GPU simulators, research directions, reliability, and security. And until then, I wish you a good afternoon, evening, and enjoy the rest of your day. Thank you.